So welcome to our talk. This talk is about virtualizing IoT with code coverage guided fuzzing. So the idea is that we want to build some smart guided fuzzer to find bugs inside embedded system. Okay, so this talks about our teamwork research between my friend and me. So my name is Quynh. I'm working in Nanyang Technological University in Singapore. So my main research areas focus on low-level stuff like operating system, virtual machine, binary analysis, and so on. So at the same time, I am the author of few reversing framework like Capstone disassembler, Unicorn emulator, and Keystone assembler.
Okay, this is me. Everybody got your badge? Some of you got your badge, right? I'm me and my partner outside.
Nice badge.
Come on. we designed the badge for Amsterdam, for Singapore, for Hack in the Box Beijing, and now Dubai. Okay, I'm from JD. We got a research lab over there. Of course, we designed a badge. They call me a broker in Hack in the Box. So I'm the Hack in the Box crew member. I do all sorts of weird shit together with them. Okay, and then I also play CTF. So this talk will be from me and Quynh. So we'll be talking about how we build IoT fuzzer together with virtualization technique. Go on. Yep.
Okay, so here's our agenda. First, we take a quick look at the concept behind guided fuzzer and how we want to build this one to find bugs in embedded system. So we need to do a lot of things. We need to emulate the firmware. We need to build our own DBI, and then finally you can build our own fuzzer. And if you have time, we have some quick demo, or if you do not have time, you go to our Armory session later to see the real demo. Okay, this talks about fuzzing. So the idea behind fuzzing concept is very simple. You have a program that processes some input. So you want to find a special input that can trigger the bugs inside this program, right? So the idea of fuzzing is that we randomly modify the input and feed this input to the program that we want to test. And when the program is running, we monitor the program to see program has any abnormal behavior. So we focus on bugs like memory corruption or information leaking. We have vulnerability or zero day finally. So there are many kinds of fuzzer, but all of them focus on how to generate the better input so you can exercise as much code as possible in the huge code space of the space of the program. Okay, we have a few kind of fuzzer here. So actually you have a spectrum. On one end you have the black box fuzzer. On the other end we have white box fuzzer. So black box fuzzer is kind of dumb fuzzer. So when you feed the random input into the program, we monitor the program from outside without any insight on how it works when the program runs. So the other type of fuzzer is white box fuzzer. So before we fuzz program, we use many heavy and complicated program analysis technique to understand the program structure. So we know very well how the program passes the input. So based on that information, you can produce better input for the fuzzer. So you can see that black box fuzzer is kind of dumb because we do not know how it works inside. We just try to produce some random input and hopefully the program crashes or something. On the other side, we have white box fuzzer, which is very smart because it knows very well how the program works. So it can, in theory, it can generate a very good input for the fuzzer. Unfortunately, white box fuzzer is very nice in theory, but in fact, because it uses two complicated techniques to analyze the program, in turn that's very slow, too slow to run, and it's not very effective. So here comes the third type fuzzer, which is gray box fuzzer, something in between, not black, not white. And we also call this one coverage guided fuzzer, and this is our main focus in this research. Okay, so here's how the guided fuzzer works. So the idea is that we do not run the original program, but we instrument it. So we run the instrumented program in our fuzzer, not the original program. And because the instrumentation in the program we run, it can report back to the fuzzer which code the program already exercised with this input. So based on that feedback, the fuzzer can produce better input in the next run. So in the next run, the program can exercise another code, a new code. So turn out that this kind of fuzzer is very effective, and because it's smarter than a black box fuzzer, but it's much lighter than a white box fuzzer. So it's much easier to set up, to use, and actually it found a lot of bugs. And one prominent type fuzzer of this type is American fuzzy loop or AFL, which found a lot of bugs recently. It really changed the game. Okay, so the idea is that guided fuzzer works very well for powerful system like PC, right? So the idea is that now, if you want to build guided fuzzer to fight bugs in a much less powerful system like embedded system, how we can do that? So in this research, we want to build our guided fuzzer for embedded system, but turn out that there are many issues. Three main issues you want to bring a guided fuzzer to embedded system is that first one, we do not have good support to run guided fuzzer inside the embedded system. The second issue is that the embedded system are usually not open source. You don't have source code. And the last issue is that we lack support for embedded hardware. Okay, we go into each type issues. The first one, you can see that for embedded system like network router, IP camera, and so on, we do not have built-in access. You cannot access to the system, to the device, right? They do not provide you the shell access. So without shell access, we cannot easily introduce our own tune to run on that on the embedded system. Because inside the embedded system, even somehow if you can access to the system, we don't have compiler, we don't have any development tools, we don't have debugger, and do not have any analysis tool running inside that. So the second issue is that, okay, embedded system usually come without source code, but all the existing guided fuzzer like AFL, they rely on the source code to be available, so they can build the instrumented program based on that. Actually, fuzzer like AFL, they support emulation mode using like Quynh emulator, but turn out that you cannot really run AFL on many Quynh program. I mean, on many targeted binary, because Quynh is not very good on supporting many kind binaries. So the third issue is that most fuzzer are built for Intel CPU only, which is very powerful. But nobody builds a fuzzer for much poor system like embedded system. And because all the embedded systems, they do not run on Intel CPU, but they run on different CPUs like ARM or ARM64 or MIPS or PowerPC. So you can see that all the existing guided fuzzers, they do not work for embedded system.
Okay, so it's just like your badge. We do have a secret menu down there that it's for the last thing that we wanted to announce after the talk. So what happened today is this session will be our final session that we did for DEF CON group. We did for BruCon, we did for Hack in the Box Beijing, and today we'll be pretty much focusing on the emulation part. That is number one. And number two, it's we're going to focus a bit on, we're going to talk about the bugs that we found And number 3, that will be a little bit summary for all the talks that we have been through based on this topic. This is a very big topic, so we decided to split into a couple of talks. And then this will be pretty much the summary and focusing a little bit more on the emulation part. Okay, so what I'm going to do now is we're going to talk a little bit on how the history of IoT devices come around. Okay, so you have 2 words that you keep on hearing from all your friends when you talk about IoT. Okay, don't talk about the communication part. Don't talk about the firmware whatsoever. You always heard of a MCU and a SoC, right? So it's basically a processor that scaled down from a PC, right? I used to love that picture when we used to have ISA port, PCI port, and it's pretty much scaled down everything from display, from graphics, from controller, from whatever thing there is, scaled down to one small little chip that you can see from a badge. All right. Of course, this is a MCU. And you have SoC chips, all right, and that is where you scale down. They put everything so small into one small little chip and a very low power device. That is what we call as an IoT device or embedded system a couple of years ago. So the requirement to do hardware hacking, right? You have car hacking village, you have IoT hacking village, you have all sorts of hacking village over there. But in order for you to do this, what do you need? That is pretty much important, right? You need to know at least a little bit of hardware. You need to know which part of the board belongs to what. That is what the badge is for, by the way. All right. And you need to know Linux command. We used to have this nice word called asterisk NIX. I'm not too sure how many of you guys actually remember that, all right? It stands for FreeBSD, it stands for Linux, it stands for Unix, okay? Asterisk NIX. So that is the thing that you need, okay? So, yeah, I keep on telling my friend that there are a lot of people, even when we are outside in the batch hacking area, they ask me how to start hardware hacking. I told them, if you decided to start, that is nowhere for you to go back. It's always in the dark side of the force. So if you decided to start, you're going to spend money, you're going to do it properly, or you don't start it, right? Yeah, my friend down there is smiling. It's a dark side, okay? So let's get started. How do we go into this entire project? It's just basically, we had a discussion and then we thought, we looked at the CVE, we did a search for some router, and then we noticed that each and every router, each and every CVE that they produce, they tie to one specific version. It's very, very weird. If I'm a vendor, logically, if I design a hardware, if I design a firmware, I will put it throughout my entire series of whatever product that I have. Okay? So, and then we thought that we should try to look for the same bug that never appear on the CVE on a different model, and we can cheat some CVE. Of course, that is not the initial intention, but that is what we wanted to find out. Same bug, same CVE, same description, but different model. That is what we wanted to do. And then we strongly believe that most of the firmware, most of the hardware devices, even different model, they will be running the same firmware. So it should have the same bug appear. So, how do we get the firmware? We bought some devices, and then we tried to download the firmware from here and there, and we discovered there are few places you can get the firmware. Number one, of course, you can use a hot air gun. Blow down the small little hard disk. Okay, you don't have it over here. No, you don't have it over here, but this is a 8-pin chip, okay, that stores the firmware. You can actually blow down the thing, put into your card reader, put into your chip reader, extract up the firmware. That is number one if you have the hardware. If you don't have the hardware, very simple. Go to the official website, try to download it, okay? And throughout the way, try to source where is the original SDK comes from. That is the fun part. You will notice most of the IoT devices will come from 1 or 2 SDK, and that's about it. Okay? And then the last place that you want to find is there are some hackers group, all right, some researcher, they will put the firmware, the modified firmware and the original firmware in their GitHub repositories. So go and get it. So that is what we thought. Okay, originally we try to download the firmware, we patch the firmware, we put in our fuzzer, and we are good. But we noticed that we have all different sorts of things that we need to worry about. We have MIPS, and then if we need to run things in MIPS, we will have a lot of issue with all the different kind of requirements inside MIPS. And we have ARM. That is good enough. That is fair for a lot of camera that actually runs ARM. MIPS, you can have small little devices. And the best part is there's a lot of sound box. Okay, everybody knows the sound box, right? The one that you talk to, they will respond. They will do whatever things that you ask them to do. It's running on ARM64. So whenever we discovered all this architecture, we know that we need a little bit more things if we need to fast a very big scale of IoT devices or embedded platform. So we've tried to focus on ARM. That gives us a bit more flexibility. Okay, and we discovered we are bumping another issue. Okay, we have some IoT hardware runs on very old Linux version. Trust me, it went even further than 3. It went back to 2.6. That is one of the very common. Yeah, my friend is knocking his head, 2.6 kernel, right? When I was 6 years old. I'm joking, I'm not 6 years old when it was 2.6, okay? So yeah, it was kernel 2.6, and all the ARM platform from ARM v5, ARM v6, version 7, and then version 8, they added as and when they feel happy, they wanted to add in the instructions. So they put in the instructions, they add in some instructions, and this is not a bad thing, okay? This is not the bad thing. This is a bad thing when you want to write shellcode. So if you do a shellcode and then you discovered after you finish your shellcode, you can run on whatever devices, your Raspberry Pi. If you try to emulate the firmware on Raspberry Pi and you write your shellcode, you will find out your shellcode will not be run because your IP camera is running on ARM v4, v5, that they don't have the instructions that you're supposed to run during that time. So that is the issue that we found. So we went into fuzzer, we tried to write shellcode, we tried to do exploitation, and these are the issue. And we discussed about this issue, and then we said, the best thing to solve this, we need to emulate the firmware. Full scale, different CPU architecture. We can do a newer firmware, we can do a newer kernel, but let's stick to the architecture as close as the embedded system having during the time you bought. So, yep. We did a quick Google search. Okay, we are a bunch of lazy people. We don't write code before we do a quick search. So we search on the internet. We discover that a lot of people, a lot of CTF challenge, okay? When they receive an ARM challenge, they receive a MIPS challenge, they will run with QEMU userland mode or QEMU userland static. This is how they call it. All right. So you can see this is how they run a BusyBox together with a change root. All right. It's good. It's the most easiest way to run binary on different architecture. But when you need interactions, there are a couple of IoT devices. Okay. They require you to run when there is a camera exists. They look for cameras, they look for sensors, they look for motors. Okay, we have seen some IoT a camera running on motors, or a refrigerator looking for a temperature sensor. That is the things that we bump into. And then you cannot do two binaries interaction together with a QEMU user mode. That is the pain that we are facing. So, and we thought we wanted to do a full, complete QEMU simulation, but we tried again. We tried to search from Google. We discovered that there is couple of emulation tools which is already available outside. Okay, and it's not going anywhere. They stopped around 2006, which Scotch FS is still the de facto standard. people been moving to JFFS and then you know some other weird things that they are running. It's not really helping us to do anything what we want over here. So when there is no solution, I guess we need to build our solution. That is how we started. Okay, he got a fuzzer. He built Capstone, he built Keystones, and then he built a Unicorn engine. And we wanted to have a fuzzer, and we don't have an environment. Previously, we thought, yeah, using the hardware or try to use some QNU, it works, but apparently it not. So we went a bit further. And we discovered the original embedded system or on the hardware will not give you as many CPU as you want. Normally they will run in 1 MIPS, 2 MIPS, okay, 2 cores processor for MIPS, for ARM, or even 4. By emulating firmware, we thought we can do a little bit more. We can add in more RAM as and when we want, okay, and more hard disk space for sure. We can do 1 gig, 2 gig, 3 gigs, 4 gigs. All depends on how we want to run the system. So, more resources, more power, more easier for us to do our fuzzing. So that is where we started to build everything piece by piece just to get the fuzzer running. Okay? So 1, 2, 3. That is what we wanted to do. And the objective is pretty much simple. We wanted to run the firmware, to run the core services, bring it up, able to access the web interface or whatever interface that they are providing, and we can start our fuzzing. So a lot of time, that is only one process that you want to run, and there are a couple of times we discovered you need to run 2 or 3 processes. They will interact with each other, and that is what we are trying to do. That's what we try to go for. Okay, so there are 2 routers over here, 1 process listening on the port. But the only thing is, we need to worry about the hardware interactions. So one thing very common that we discovered during the entire research, okay, one thing very common, it's the processors that's supposed to talk to your web, that's supposed to talk to your application, your mobile apps. It's one independent process, and it will communicate through NVRAM or communicate to a UDS, Unix domain socket, on the other process, the other independent process that talks to the hardware. So this makes us very easy to patch most of the stuff. So these are all the small little issues that we try to do. So in order to boot up, you can see it was a one-liner, a very short QEMU line to boot up the entire system. And in order to boot up ARM, in order to boot up ARM64, in order to boot up MIPS, okay, that is more things that you wanted to do. Of course, together with your source net for your IP tables, that is to enable your software to communicate outside. That is for you to do a bit more activating the system. Okay, of course, activating with the actual server or activating with the server that you try to put it up. Okay, one good thing about ARM, not MIPS, we cannot really do it with MIPS, but one good thing about ARM is there is a Vert.io support, okay, that enables you to do a very close to actual acceleration, just like your x86, okay? Not 100%, not 80%, but it's fast enough with and without the acceleration for ARM inside your x86. Okay, so after you run the firmware, after you put in the firmware, after you boot up your Linux, okay, the first thing that people always argue is, do you need to run it on the old kernel or the new kernel? That is what we saw. Okay, apparently for most of the IoT devices, we have tested more than 70, 80, or even 100 IoT devices. Most of the firmware that we receive, it enables to run with the new kernel without any issue. Okay, that is just depends on how you want to patch it, and you just cannot do it with chroot. A lot of times, if you run together with chroot, you try to run your GDB, you try to run your GDB server, it don't really work. And sometimes you want to do your syscore trace and all these things, it just can't allow you to do. So chroot, it's able to for you to get your things out, but in order for us to run our fuzzing tools, if in order to do our things, it's not easy for us to get into that situation for us to put in our fuzzer to run. So we need to run outside chroot. Okay. So the first problem when we able to build, when we try to move everything out from the chroot environment into the QEMU systems, the first thing that we found is found not found. We try to execute a command, then it tells us we are not getting anywhere. So if you do a trace, if you do a dump, you try to run a command, it will tell you no such file or directory. It specifically tells you that the command that you try to run, it's not there. And after some tracing, we discovered that it looks for one Linux library that you need to have that specific file name in order to run. So the file not found is not referring to that particular binary that you are looking that you're trying to run, but rather the base library that they are looking for. That is the first problem that we found. And along the way, we solve a lot of SO issue. Okay, we try to link them one by one. This is one of the soundbox that we are testing. We try to fuzz the soundbox, and we try to link one by one, and then we need to fit the library in there. So once we able to fit, then we will be able to run the binary. And we have most of the time we will have some segfault without very clear messages. It will not tell you is that a file missing or is that whatever error that is, but you need to trace stage by stage. Goes back to the original the original message, all right, and try to find out what is missing. Sometimes it's just a library missing. When we are doing some camera, we discovered there is quite a fair bit of lib decode library which is missing, and it will not exit straight away. It will run other commands, and then the other commands try to look for the thing for the second time, then only it exit. So it will not tell you which one exactly does it look for, but you need to trace page by page for you to get your information. And then we have some NVRAM issue. So what do we have in this NVRAM thingy? It's like what I mentioned just now, that is a lot of process that only interacts with the hardware, but not your mobile apps, not your web application. So what do you need to do over here? It's you need to fake an NVRAM. All right, NVRAM is for you to store your configuration in your IoT devices. Right, you need to fake your NVRAM in using a Unix domain socket, put in all the data, and when you try to run the process, they will go and read your Unix domain socket, extract out your configuration, and that is where you can run your program smoothly. So you patch your file not found issue in order for you to run outside chroot. You patch the missing SO issue. You patch the NVRAM, you try to lie over NVRAM, and one of the very common things that we discovered, okay, it's either you run on NVRAM or you just write some very quick Python script for you to run it. So one good thing about emulating firmware to analyze IoT devices is you have your apt-get. You can install whatever things, your Python 3, your Python 2.7 into your virtualized environment and run whatever code that you try to lie over the binary. You try to cheat the binary for you to go through whatever things that you wanted to patch. So NVRAM, it's one fun thing that we see. 99% of the IoT devices, when they access NVRAM, they will not access NVRAM directly. What they will do is they will get the original SDK from the chip maker. They will do the Unix domain socket, and they will connect to the Unix domain socket to extract out the NVRAM. So you don't have to patch your NVRAM. You don't have to emulate your NVRAM, but rather write a Unix domain socket file with your Python, simulate the NVRAM and run it. That is the easiest and the quickest way to patch it. Okay, so that is a fake NVRAM, and that is the Python script. Okay, a custom interactor, fit in whatever thing that they request for. If they ask for IP address, give them an IP address. If they ask for a port, give them a port. If they ask for serial number, give them a serial number. As easy as that. Okay, BR0 is bridge, not brother. Okay, so for IoT devices, you can see most of the time the binary will ask for the bridge device interface. Just build one, okay, with your bridge CTL command. Create a bridge, link it up. When they look at the BR0 interface, then the process will continue runs, and that is how you can run your process. Sometimes it look for Wi-Fi devices. That is even simpler. It's either you change your ETHO to WLAN0. You can do that in Linux very easy. Or you build a bridge interface, name it as WLAN0, then all the magic will work. Very, very simple. Okay, so if everything else fail. If everything else fail, buy a copy of original IDA. Yes. And then a couple of years back, we do have this thing called, what was it again? Key patch? Yeah, key patch. Trace the binary, alright? Patch whatever things that it doesn't look good, okay? So you can patch BEQ to a BNE. You can patch your BGT to a BGT is greater. You can patch it to a BLT. So that is the thing that you want to redirect the execution flow, okay, in order for you to run. So you have your branch. You normally don't do branch, okay? The program fail is just because of the decision it's not right. They are looking for something and they don't have that something and they crash. So what you need to do is you don't jump directly, you don't branch directly. What you need to do is you need to patch the decision making process in order to go to the another sub process, move it to the other way, so that it's where you can start to move to the next step and next step and next step. Okay, and trust me, most of the after you fix the bridge, after you fix the NVRAM, after you fix the Wi-Fi, most of the IoT devices, once you finish this, it's only somewhere around 8 to 15 patches, 8 to 15 bytes. You need to patch on each and every binary for them to spawn the process. Very, very easy and very, very quick. Okay. So, that is the emulation part. Then we move to Scorpio. You have 10 minutes.
Okay, 10 minutes. Okay, okay, the next part is how we build our fuzzer, because given now that we can already run the binary that we want to fuzz to 5 bucks from the firmware. Actually, we already gave many talks on this topic in some other places with a lot of details. So you can take a look at our published slides. So here I just quickly summarize what we did. Okay, so the next thing is that we have the binary, firmware binary, the program, some binary programs that we can already run on our virtual machine. Now how to 5 bucks, how to build fuzzer for this. So remember that guided fuzzer, mostly they rely on the source code to be available. So for example, AFL fuzzer, you need to provide the source code of the program you want to 5 bucks for AFL fuzzer. So it can use AFL compatible compiler to build this program. And at the output, you have instrumented binary that's compatible in AFL. And we run this instrumented binary on AFL fuzzer. However, we do not have source code, right? Because embedded system usually do not give you source code. We only have the binary. So how to build our guided fuzzer without source code? So turn out that we only need to have the instrumented binary to run on the fuzzer, right? So we decided that we do not have source code, but if we can instrument the binary at runtime, you can still build our guided fuzzer for this binary. And that's what we did. Okay, so to summarize, we need we need to use some dynamic binary instrumentation framework to build our fuzzer first. So the idea behind DBI is very simple. DBI is a method for analyzing binary at runtime by injecting some extra code into the program at runtime. And this extra code do some things that you want to do, and it's run as a part of the original program. So however, by introducing your own code into the target binary, you need to do everything to make sure that you do not change the behavior of the program. So here's a very simple illustration of the DBI. So we have the original code, which has 4 blocks, 1, 2, 3, 4, right? Now we want to instrument after block 1 and block 3. So to do that, we inject our own code in block A and block B after 1 and 3. So instead of running 1, 2, 3, 4, after instrumentation, you run 1, A, which do something first, and return, we run 2, 3, and next we run our another instrumentation in B, and after that we return and we run 4. But anyway, remember that A and B should not change the behavior of the program. Okay, so there are a few types of DBI techniques. The first one is called JIT, just-in-time translation, which is used by well-known DBI like Van Green, Dynamo Rio, or Pin. Those DBI, they use some very complicated techniques, so they translate the program at runtime, and instead of running the original code, they translate the code into another buffer, and they run the program from the buffer. They do not run the original code. So, turn out that JIT is give you very good control on the code executed, but it's very heavy and very complicated in design and in implementation. And this is the reason why on those existing DBIs they have many limitations, because it's too hard to do. So we decided that we do not want to do JIT, but we use our own technique, which is based on hooking technique. And hooking is another kind of DBI, but it's much more simple to design and implement. The downside is that hooking technique gives you less control on the code executed, because you need to know in advance where to instrument the program. So there are 2 main types of hooking mechanism. The first one is inline, as you can see in the screen. So we see that this inline code injection, we put the instrumented code directly into the program after the code you want to instrument. So the idea is that we put the instrumented code directly into the code and inline with the original code. So the idea of this technique is that it allows you to instrument anywhere. So there's no limitation on where you can instrument. But however, the downside is a big downside is that you can see that, okay, the original code is here, 1, right? Now we instrument it, 1 is still here. It's still in the same place in the memory. But because we put our own instrumentation code here after 1, and after this code is running, we need to execute the original code in block 2 here. And you can see that the position of block 2 is shift, right? It's not in the original place anymore. 1 is still in the original place, but 2 is moved behind. So we see that all the block behind A is moved. 2 is not at the original place anymore. Same thing for 3 and 4. So the inline hooking technique is good, but it requires you to move a lot of code in the memory. And this makes the techniques very complicated. So we decided that we did not do this, but we adopted the second approach. It's called detour injection. So the idea is that we do not put our instrumentation code in line with the original code, but somehow we override some code some code here in the original code, and we jump out to our callback, which is the instrumentation code. So we see that after one, we jump out to another place and we execute our callback. And two, you see that two is still in the same place. Three is still in the same place. But after three, we jump out to our callback, which is like elsewhere in the memory. And four, you see that all 1, 2, 3, 4 are still in the same place. We do not ship code in the memory. So that's the idea. So we put our instrumentation code into the callback, which is executed when the program reaches the place where we want to instrument. So the limitation of this approach is that there's some place we cannot instrument using this technique. For example, if the basic block we want to instrument is too small, we override that basic block. But when you override the basic block, we can override to the next code after this basic block. So you see that if the basic block is too small, you can override to the next code after that basic block. Okay, but the advantage of this detour technique is that it's much easier to design and implement. So that's why we decided to go with this way, to build our own DPI using detour injection technique. So here's one example. Okay, actually, detour technique has offer many choices. There are many ways to do that. So here's one technique. So you see that. So on the left side we have the original code, right? Now we want to instrument here at this instruction. So what we do is that we allocate our own buffer, which is executable memory, and we call the buffer trampoline memory. So it's in the middle here. So we want to instrument here, right? So we override this place with our own code. So our own code will save the context because branching to the callback can change the context. So we save the context first. After that, we jump to the trampoline buffer. And inside the trampoline buffer, first of all, we need to restore the context we save here after jump, right? And after that, we make a call to the callback, which is our instrumentation code. And because call can modify the CPU context, we need to save the context first here. After that, we make a call to our callback. And when you return from the callback, we restore the context here. And the next thing to do is that because we override the instruction here, right? So we need to execute it somehow. To do that, we copy this code. You copy this instruction from here, to the trampoline memory buffer. One thing to remember here is that usually when you copy code from somewhere to somewhere else, it still works. But there's some special instruction, some very sensitive instruction, which is sensitive to the position inside the memory. For example, on the relative instruction, the relative jump, relative memory access, when you move it from somewhere to somewhere else, it doesn't work anymore. So, to make sure that the original code still works, we need to relocate the instruction. We need to rewrite, to modify it somehow in some cases. And after that, we jump back. So you can see that in the original code, we execute instruction and something, right? When we instrument this code, we save the context, we jump here, we do not change anything, and somehow we can still run our code back, and we jump back here and continue to run. So you can see that when we instrument the binary, we do something extra. We run our extra code back, but we do not change anything in the CPU context of the program. Yeah, there are a few other type detour instrumentation technique. First of all, this one is that it's a bit different. So you see that the first one we use the trampoline buffer, right? Trampoline buffer. But this technique we do not use trampoline buffer. Instead, we override this original instruction and we save the context, of course, because branching can change the context. But this technique we do not use the trampoline memory buffer, but we jump directly to the callback. So there's no more intermediate memory buffer for this technique. And we restore the context after jump, and we relocate the instruction here, and somehow we execute the code back here. And after that, we jump back here. This is another type of detour techniques. The next one is a bit different. So the first two types, we use jump to branch out, right? But jump is not the only technique to branch out. We can also use cone to branch out. So that's the third type detour injection. So we see that, again, here we use Chamberlain memory buffer. But instead of jumping, we cone to the Chamberlain memory. So here we restore the context from the cone. We say the context before we make the cone to the cone back, which is our instrumentation code. On return, we restore the context. We relocate the instruction, and we return from the cone here. So we come here after the cone. So the third type, detour injection, is different because we do not use jump, we use cone. The last type, detour injection, is we do not use Chamberlain memory again, but we still use a cone for branching. So you can see that here we cone to the cone back here, right? We don't use a Chamberlain buffer in this case, and we do the same thing like in the last case, and we return here after the cone back. So the idea is that we have many different kind of techniques for DBI instrumentation. So at the time we decided that we wanted to build our own guided fuzzer for embedded system. We try to find some DBI that can work for embedded system. But turn out that nothing works because all the existing DBI has many limitations. They are limited on platforms. They're limited on CPU architecture. So for example, all the popular DBI you can find on the internet now, like Dynamo Rio and Pin, they are all limited for Intel CPU. Pin and Dynamo Rio, they do not support any other CPU besides Intel CPU. But we want to build our fuzzer for embedded system, which run on ARM, ARM64, MIPS, PowerPC, and so on. The third problem is that on the existing DBI, they do not support many cap instrumentation, I think, like that I already presented. We have 4 type instrumentation, right? But on the existing DBI, they do not support all of them. And finally, on the existing DBI, they provide you some very friendly API for you to build your own instrumentation tool on that. But they hide many details inside. They do not expose many internal things, in the internal techniques. So in result, you cannot do many cap optimization to speed up your instrumentation, which is very important for the fuzzer. So we decided to build our own framework for DBI, which is called Scorpio. There's some main advantages offered by Scorpio framework. First one, Scorpio is a low-level framework, so you can build your own instrumentation on top of that. It supports own cap platforms. Scorpio works on Windows, on macOS, on Linux, on BSD, and on everything you can try. It supports own cap CPUs. It works for Intel, it works for ARM64, for MIPS, for Spark, and for PowerPC. And it allows own cap instrumentation that I presented. And it's designed to be very easy to use, but support own cap optimization. For some special setup, it can be like 100 times faster if you compare with other frameworks. Yeah, so here's very high level overview of how the Scorpio is built. So we see that on top of Scorpio, you build your own instrumentation, and it provides an API for you to build your instrumentation tool on top of Scorpio. And we support own cap operating system and own cap CPUs by implementing some middle level layer to hide away all the details of the platforms and the CPUs. So on the operating system, on the CPUs, comes into the framework as a CAP plugins. This is how we build and support own CAP OS, own CAP CPUs. Yeah, there are many details on how we build that. We need to support own CAP operating system. Need to support own CAP CPUs. Need to save restore context, and it depends on many things. It depends on CPU, depends on calling convention, and so on. Yeah, there are many other things. You can take a look at the slide later. So it's quite complicated to build the Scorpio framework. Just one reason why Scorpio work on own CAP CPU and own CAP operating system. Because Scorpio is built on two other frameworks for disassembler and assembler. And for disassembler, we use a capstone framework. For assembler, to rewrite code for relocating instruction, we use Keystone assembler to rewrite the code. And because Capstone and Keystone, they are working on many CAP operating system and many CAP CPUs, and Scorpio built on top of that can work on the operating system and all the CPUs I show you. Okay, finally, after a lot of hard work, we have our own DBI that support own CAP CPU architectures. So we can start to build our own guided fuzzer for AMD system. Okay, so the idea is that there's some future of our fuzzer. Okay. Okay. We build on top of IFL fuzzer with Scorpio DBI for instrumentation. And finally, the target binary is instrumented at runtime. It can be run on the IFL fuzzer. So there's some more details about how we build our own fuzzer. You can take a look at the slides later because we are running out of time.
The reason why we skip a couple of slides just now, it's already presented in the previous talk, and the reason why we keep the slides is just for you to take a look later, and just for your notes and for your reading purposes. Okay, so in GeekPon 2018 Shanghai, we took part in the competition, and then we actually found quite a fair bit of bug. And all this bug is being discovered in a GeekPon. I don't think the IoT vendor already patched the bug. The reason why they never patched the bug is, of course, they are still relying on the SDK original vendor to patch the bug. That only they patch the bug. So it's a very complicated husband and wife issue. That is how I call it. Yeah, you know that well. Okay, so. The first bug that we disclosed and we actually arranged. We have quite a fair bit of our IoT bugs. When I say quite a fair bit, is each and every device that we actually touch, we found a vulnerability or a couple of vulnerabilities, and we kind of sort out a couple of them to make the event looks nicer. So we have a buffer overflow bug, found it using our fuzzer. And it's a pre-authentication bug. This is fun. Okay, this is fun. It's a buffer overflow bug. It's a address. We managed to overwrite the stacks. We managed to overwrite the address. All right, and we have one dead issue. It's the watchdog. Every time you overwrite some address and you never exit properly, the webcam will reboot. So it's not that easy for us to get way to actually randomize and try to brute force the address. Okay, so we do it in an emulation. So we extract out the firmware. So how do we extract out? This is a very fun camera. You cannot find any firmware on the official website. They don't even have an official website for whatever reason there is. So what we did is we extract out the firmware from the chip reader. We kind of rearrange the partition, and we disable the watchdog, of course. That is where we started to find the address, we patch, and then we try to run inside the thing. It's ARM v4, so we need to emulate a complete ARM v4 architecture, run the binary, okay, and then we put in all our tools, our debuggers, our whatever thing there is, and that is where we started to build the shellcode. We got a shell for this. That is one of the bugs that we disclosed in Shanghai last month. And we got another IoT camera from a very, very big vendor. They got website, they got everything. It's the thing they call the baby cam. You know, the cam that you bought to monitor your baby if they cries and all these things, you know. So we found it on the emulation, not really the fuzzer, but we noticed that once you connect to, once you run the firmware, they will listen on UDP port, and the UDP port actually allows you to run certain command, and one of the command is called exec. If you connect to the device, you run exec, it will not show you anything. But after you emulate the firmware, you put in exec, you can see exactly exec_ls inside your emulation terminal. They actually shows you the command is being executed and you got the output. Of course, we put in a telnet, we inject a telnet into the run script, and we got telnet, okay? And we also have a Chinese-based Wi-Fi router, and this is actually quite fun. They do have two versions, one international version and one Chinese-only version, okay? Same bug, same way to trigger, and one on the international version, they name the function as, again, exec. And in their Chinese version, it's USB something. So I'm not too sure why they want to do it like that, but yeah, we found a bug. Again, if we try to run it on the web, if we try to do a command injection using curl or whatever thing there is as a black box, you will not be able to see the execution. But if you run it in emulation, you can actually run a uname, you can chain command. So during the computation, we built a URL. We try to chain all the command. We get a shell. We inject our packet in there. That is how we get the root. So all these things we will be demonstrating tomorrow at the Armory exhibition site. Okay. So the conclusion over here, it's when we do our emulation, we do have a firmware emulation. That is what we wanted to solve if we need to build a very, very strong fuzzer. Then we wrote Scorpio DBI, and then the last thing is we built a guided fuzzer for embedded system. So 1, 2, and 3 by using emulation and by using how we patch the code and we sift the code. And the last thing is how we run the fuzzer for emulation framework. The thing over here is we try to build a new system. All right, that is our next year project. Much more advanced than with these three combined. That is what we want to achieve next. So the conclusion is, we do this conclusion like so many times, so screw it. I want to do my announcement right now, okay? My secret menu. Okay. Capstone 4.0. Do you want to talk about it, or you let me talk, do the talking?
So, okay, I'm the maintainer, the founder of Capstone Disassembly project. So we started Capstone in 2013, which is 5 years ago. And Capstone turned out to be pretty successful. And it's a foundation of many reversing and so on frameworks on the internet publicly, and also many private ones. And currently you have the latest release 3.0.5. And version 3 we released in about 4 years ago. So it took like a few years and a lot of work. And we are going to release Capstone version 4, which is longing by a lot of people in the community. Next month, about middle next month. It took us so much time because, developing and maintaining is very tough, and we do this in our spare time only, and we are very slow, and that's why. But fortunately, we have Capstone version 4 out next month.
I still got the screenshot. Quynh specifically told me, I asked him why 3.05 until now there is no advancement to 4.0. He told me it's lazy. You said it's lazy, right?
Yeah, kind of.
Okay, so the second thing we want to announce is from Amsterdam this year onwards, we do have a badge, a very square badge for Amsterdam, and we have a lion looks-alike badge that runs on STM32, STM32F103 that pretty much looks alike, pretty much same architecture with the one in Amsterdam. Okay, that is for the Singapore badge hang in the box. All right. We had a party, and then we have another batch that with a different kind of cool games in there, which still runs on STM32. And for Beijing, what we did for Hack in the Box Beijing is it's a small Wi-Fi router that builds into the entire batch. Okay, I cannot say this in Beijing. It's just purely because that batch is supposed for you to install your VPN and for you to get your Google. I'm out of China right now, so I can mention that. That is the entire purpose for the batch in Beijing, okay? And this time round, you have this thing. Okay, runs on LoRa, okay, and then designed by my friend. He's supposed to come here and comes out of the entire stage, but he's not here today. I got no idea why. So all this project from Amsterdam, to Beijing, from Singapore to even today, we are open sourcing all the badges PCB or how we design the badge. Okay, everything is in eager format, so it's not whatever PDF that you need to redraw and all these things. You put into your bot software, you can do your modification and together with the source code. Okay. For Dubai batch, we're gonna do it maybe tomorrow or day after tomorrow, but whatever previous conference for Hack in the Box and for our party, all the source code and the batch is already on GitHub. Just go to hackersbatch.com and you will get all the information. So, questions before we end? The guys at the back gonna kill me because we 2 minutes more.
We'll take the one on the left first from Professor Kang.
2 questions.
And then Swami. Oh, wow. Okay.
No badge for you, sir.
So I have a question about the emulation part. So
Right.
Right now, I'm not sure whether you ran into a situation that an application just do an I/O port access.
Yep.
I know you can probably use your way to patch it, but sometimes the later function might depend on the value you read out from the I/O port. Have you guys run into that problem or have a solution for that?
The problem with the hardware is most of the time that we discovered the problem with the hardware is it's not the core process that runs on the listener, the HTTP or the one that interacts with the app that actually getting the I/O. It's something else in there, the sub-process or whatever thing there is. So as long as you can emulate the communication, that is what we do. It's either Unix domain socket or we have seen some Netgear routers actually communicating through a text file. So patch that text file, make that text file, mix that UDS, and the thing will work. Right.
And the next question from Somil.
It's a subset of the same question, but I was curious about the Unix domain sockets for the NVRAM.
Yep.
So basically what do you do? Just grab the NVRAM of the MTD partition and pipe it over a Unix socket?
Well, the thing
Like
is,
in
with
raw?
NVRAM, you can actually listen on the request. Okay, and we got our own script that actually generate and we randomize the data and all these things. It
Okay.
will not crash immediately. We will fit different kind of data into the NVRAM to get it. That is the easiest way. Of course, that is the most simplest way if you don't have the hardware.
Oh no, like if I have captured the NVRAM from the hardware itself, then we can give it the
then
genuine
you
data.
can do it. Because for you to get it from the hardware itself, there are 2 things you need to do.
Yeah.
Get the hardware,
Yeah.
extract out the chip,
Yeah.
get out the firmware,
Exactly.
patch the firmware with Telnet,
Yeah.
solder it back, then you can extract out the actual NVRAM. But most of the time, we are cheapo, so we don't have the hardware.
This is the last thing I expected you to say.
Right. So
Anyway.
yeah, we feed the data randomly.
Right. Okay.
Right.
Okay. No worries. And second is, where's the Scorpio framework, man?
Okay, I'm going down.
Okay, I got
I'm
many
not going to answer
questions.
that.
I got the same question from many people. So the idea is that I am going to release that to the public, but for now, my organization asked me to hold that for a while. So I cannot promise when, but eventually it will be yes. Maybe I think sometime next year.
You know,
In Amsterdam.
You wait there soon enough. One day when God answer my prayer, we will release the framework.
And there you have it. It will be in Amsterdam next year, Hack in the Box.
Yeah, hopefully, yes. Or before that, yeah.
Oh,
Yeah, man. Or before that.
Oh, thank you very much. Any other questions?
Thank you so much.
No?
Oh, one more question?
Nope.
No?
No?
And thank you very much, Nguyen and Quynh and Lau Kai Jern. Also, thank you very much for the badge, for the conference badge. Indeed, you've actually been responsible for the conference badges for all of this year in all 4 countries that we've had Hack in the Box, and we're very appreciative. Thank you very much, gentlemen.
More to come.